I want to quickly go through a worked example of Euclid's algorithm. And that's for calculating the greatest common divisor of two integers. In addition to that, I want to also show the Bézout coefficients. And the Bézout coefficients allow us to write the GCD as a linear combination of the two initial numbers. GCD of AB is equal to A times S plus B times T, and S and T, they're also integers. And not only that, the next thing I want to show is that S and T are non-unique for the GCD of A and B. So the example I'm going to show is going to be the GCD of a couple of integers 312 and 792. And initially we'll just do the we'll go through Euclid's algorithm, which will involve dividing 792 initially by 312. So let's do that. So 312 into 792, that will go in twice. 624, and the remainder will be 8, 6, 168. I now want to divide 168, the remainder, into the original divisor. So 168 goes into the original divisor, and that clearly goes in just the once. And remember, I'm doing another borrow here, so 12 taking 8 is 4. That would be nothing there. 6, so that's going to be 144. I now want to divide this new remainder into the second divisor. 144 into 168 clearly also goes in just the once. And the remainder there is very easy, 24. New remainder into the next divisor, 24 into 144. 144 is 12 squared, so that's going to go in 6 times and with 0 remainder. So this tells us that the GCD is 24. So GCD of 312, 792, 24. So we're done on that one. Now, the interesting thing is we can rewrite this equation as the linear combination of the original two numbers. So how do we do that? We can work our way back through these divisions here. We'll start here because this is the first place where our GCD turns up. So we'll say that the GCD 24, we can rewrite that as 168 minus 144. The 144 first turned up here, and we can rewrite that. And we can rewrite that as 312 minus 168. And we can collect up these two terms, the two 168s here. So we've got, that's 2 times 168 minus 312. 168 turned up here. We can rewrite the 168 now. 312 is one of our original numbers, so we can't rewrite that as anything. But the 168 we can rewrite in terms of our two original numbers, 312 and 792. So we've got 2 times 168, and the 168 is 2 times 312. Oops. It's going to be 792 minus 2 times 312. That's our new representation of 168. That covers this term here and minus 312 here. So now we've got 2 times 792. We've got minus 4 and another one, minus 5 times 312. And so these are our Bézout coefficients, and we've now written our GCD of 312 and 792 as a linear combination of these coefficients, using these coefficients, minus 5 times 312 plus 2 times 792, which is kind of cool. But I want to know whether these are unique solutions. Is that a unique solution? Are there any other integers for which this would be true? And if we can do that algebraically by saying our GCD of AB is equal to AS plus BT. Here's the S, here's the T, and here's the A and the B. If I rewrite this as AS plus BT plus KAB minus KAB, and K is also an integer, then clearly I've got 0 here. But what I can do is I can collect up these terms. So I can do A. If I pair those ones up, I've got S plus KB plus, now collecting up B, the B terms here. I've got B and I've got T minus KA. So clearly, equating terms with this original equation here, S and T, I've now got a different version of S and a different version of T, because these are all integers. So clearly the S and the T are not unique. Furthermore, we know something about B here and we know something about A. We know that we can actually divide by our GCD, because we know that the GCD goes into B, and we know that the same GCD goes into A, and we can make those integers smaller by doing so. So S plus K times B over GCD plus BT minus KA over GCD. And we can plug in different values of K up here and have see different combinations to get our original GCD.